There it is. Right. So if, as you recall, we were doing single source shortest paths, the SSSP problem. We did a fair deal of discussion. We had a fair deal of discussion on negative weight cycles. We talked about Bellman-Ford as dynamic programming. And then we talked about the relax operation. So just to recall, let's flip through the notes from the last time. So the dynamic programming perspective was basically given by the following recurrence. It just said that dkt is the shortest path from S to T with at most k edges. Remember, S is the source vertex that we fixed, right? And we have a recurrence for dkt. We say dkt is the min over all the in neighbors of dk minus 1 of v plus the weight of v to d. It says to get to T, you have to get there from some in neighbor. So you look at all the in neighbors, and then you look at the you look at the path, the shortest path to any one of them using k minus 1 edges, and then you take one step. Okay, so you minimize over that. You could do this, you would get Bellman-Ford. And of course, what we also said is that Bellman-Ford has a different perspective, and that is through this perspective of what we call the relaxation step. So the relaxation operation is a kind of safe operation. It maintains the invariant, and the invariant, which is given here, is that you maintain an estimate of the true distance which is never less than the shortest path distance. So you're maintaining this upper bound, and you keep trying to bring it down. And you maintain predecessors so that the predecessors give you a path with that distance. And you keep trying to improve it, right? That was the idea. And so when you have that perspective on Bellman-Ford, then you can, or rather, when you have that perspective on the invariant, you can say that let's take the relax operation, which simply says for any edge, if you can get to v via u better than what your current estimate is, go ahead and just apply that. So this is the operation. So, and we can think of any single source shortest path algorithm as a sequence of relax operations. Bellman-Ford then becomes very simple, which is to simply relax over every edge, or rather n times relax all edges, or n minus 1. Okay, so the final place where I left you with is this, which says that Bellman-Ford runs in theta of mn time. So it is quadratic or worse. And Dijkstra only works with non-negative weights, but instead of mn, it's essentially m log n. And you can kind of use fancier data structures to get something like m plus n log n, using something called a Fibonacci heap. But that's sort of beyond the scope of what I want to talk about in this course. It's going to increase the volume a bit. Okay, so I'm going to talk about Dijkstra's algorithm. I do not want to spend a huge amount of time getting into all the details of the proof, but I would like to hint how the proof works, because I'd like to finish the discussion on single source shortest paths and talk about another problem called all pair shortest paths, which is finding shortest paths between all pairs. But given the importance of Dijkstra, I should say something about Dijkstra. So let's look at Dijkstra's algorithm. So Dijkstra's algorithms, essentially you can think of as finding a better sequence of relax operations using a greedy algorithm. So this is very, very similar to Prim's algorithm for the minimum spanning tree. Very, very similar to Prim's algorithm. Indeed, it's basically the same up to some modifications on what you store. So what is the idea? So let me first draw out the idea. And once we have the idea, then the implementation will essentially write itself out. So the idea is, so let's say this is S, and there is some set capital S such that shortest paths from little s to all vertices in capital S are known. Okay, what this means is we have the shortest path tree from here. What we would like to do is to find another edge and extend the shortest path tree. So the question is, what is the right edge to choose? Which edge should you choose so that you can extend the shortest path tree? The one with the minimum weight. So that is a natural guess to take, but it actually will fail. So let's see why. So a natural guess is to say, I'm going to take the minimum weight edge to get there. Okay, so let's just say this edge has, I don't know, I'm just going to put a weight 5. Okay, so and let's call this vertex V. Suppose you commit to this decision. Then what have you, your distance V is going to be the distance of U plus the weight UV, and which is, I call this 5. And note that if you were to follow a greedy strategy at this point, you're not going to relax any further for V. You've basically committed to the decision for V and you have to move on. Now, why is this problematic?
There might be a long edge from somebody closer to us.
There may be another edge like this, U prime, where maybe this has 10. And instead, you could have gone distance to U prime plus the weight U prime of V, where maybe this was 10. Because when you commit to that edge, you're not sure which of these is larger or smaller. Right? Maybe it turned out that this was actually 100 and this was just 10. Right? So you see that greedy strategy would fail. But if you think a little bit on that, it should sort of tell you how to fix that strategy. So what is the right thing you should do? You do know all the distances from all the nodes. Minimize what? Minimize dv. Okay, so what you could do is you could say dv, you're going to say is the min over all u that's in the set S of du plus wuv. Okay. Turns out that's also wrong. That will also fail. Remember that when you follow the greedy strategy, you're committing to this path. How do you know the shortest path from here? Maybe the shortest path does something like this. Maybe there's some other vertex over here whose distance is 2, and there's 1, 1, 1, 1. Maybe all of these have 1, and there's an edge of distance 2. I hope my picture makes sense. Right? There could be, this is S over here. And S takes that, which is really short, then takes a bunch of short edges to get to V. So if you used any of the neighbors of V inside of S, because you're only saying, how do I get from S? So it seems that's also wrong. Consider every neighbor of the shortest path tree. You could minimize over all of those. Another way of putting this is, look at this edge over here. This is the shortest path. So actually, you should have committed at this edge, not to that edge, which in some sense is saying that you could essentially look at this quantity. But what it's saying is you should minimize this quantity over all V. Right? That would be the idea. Does that make sense? So
we need to update DV potentially multiple times.
You may update DV multiple. Yeah, so we have to think a little bit about how to implement this in the most efficient way. But the moment you see mins of some set, you should think priority queue. Like you can basically use a binary heap the appropriate way. So it's okay. So it's like the right idea is to consider the min over all V, which is, I guess, not in S, right? All V that are outside of all min in S of du. If you go back to your notes on MST, you'll see something very similar in MST as well. Because you're looking at a particular tree that you've constructed, and then you're saying, what's the next edge? There was just greedy. You just look at the minimum edge. Indeed, if you follow your strategy, you'd be finding the minimum spanning tree. Okay, so this seems like the right idea. Except, okay, so this is basically what you do. But it turns out this will fail if there are negative weights. It turns out this idea will fail if there are negative weights. Why? So I want you to go back to the picture, and I want you to tell me. So let's do this. I'm just going to draw this picture again. Okay, so let's get that out of the way. Okay, so what is your picture? So here's your graph. Here's S. And this is capital S. And so let's just say you did this minimization. Let's say you minimize this, and I'm going to just describe the argmin. Okay, so the argmin, so here's your V, and here's your U, and these are the argmin of, du plus weight uv, right? What is the problem when you have negative weight edges? So by the way, so I should say something. So what you could do is you could always apply relaxation on that edge. This is effectively what you're going to do. So you're only going to do a sequence of relax operations. You'll see that Dijkstra is only about choosing the edge to which to do a relaxation on. And any update will be a relax operation. My claim is, even though this is the argmin, this actually might not be the shortest path to V if there are negative weight edges.
You can spend a bunch of cost to go somewhere in the graph where there's a bunch of negative weight, and basically the estimate of the distance at the frontier is inaccurate because.
Well, you mean inside the set?
No, I mean
at this point.
I'm just saying that if there's a chain of negative 100 weights out there somewhere.
Outside is in here or in here? You mean out here?
Outside of it.
Uh-huh.
Then you might be able to go they're using a longer path, it doesn't.
Exactly. So what you could, or even simpler, so let's just say there's minus 100 over here,
Sure.
right? And then the distance to this, I don't know, maybe is like 5. And then here's an edge weight of 100. Right? And so what could happen is that if you go this way, the cost is only 5. Whereas if you went this way, so maybe this edge is, I don't know, is 10, and then this is, I don't know, maybe this is also 5. So actually this could be your graph, right? So that SU and S to this other vertex, the distances are 5. That's correct. And so when you do this argmin, you'll get that, oh, the argmin is given by UV, and I'll go ahead and commit to that in the shortest path. But actually the shortest path goes this way because of that negative edge. Because what this means is that that greedy operation essentially is nullified later on by a negative weight. Whereas if there are no negative weight edges, you know that if there's any other way of getting to V, it has to go via something where the distance from S to this other thing is smaller. So meaning, let me call this V prime. So this is, the reason why this is useful is that if you understand this, the proof for Dijkstra is also pretty easy then. So this is like saying Y is S to U then to V, our shortest path. So I'm not writing a proof, I'm just giving the argument. By contradiction, suppose not. So the shortest path, I should say a shortest path, to V goes as S to U prime, that's U prime there, to V prime, to V. Right, where this is in S and this is not in S. Right, this is where it basically goes out, and let's just say that all of this is not in S. So this is like the last time the path might go in and out. You don't know what it's doing, but at some point it's going to leave and then just stay not in S, where maybe V prime is even equal to V. Who knows? So what this means is, let's kind of work this. Okay, let me just write this out now. And say, the reason why this is the shortest path, so if this is the shortest path distance, then you know that, so this is saying that the distance to V is actually the distance to U prime plus the weight of U prime V prime plus, the distance from V prime to V. And what we're saying is, because this is not the shortest path, this is strictly smaller than the distance to U plus the weight UV. That's what you're saying, right? Because this is the contradiction. You're saying, suppose not, so it must imply this. Okay, now how do I complete the contradiction? Yeah?
du plus wu comma v is less than du prime plus wu prime to v prime?
Not less, right? It's, sorry, say that again?
Well, like in reality it's less than the...
True, right, because this was the argmin. Okay. But there's one thing that you're missing there.
And the dis is from v prime to v is positive?
Exactly. So you need that. It's non-negative, right? So you say because dist v prime to v is greater than or equal to 0. So this is the non-negativity. This is the non-negativity. Because of this, what you get is d of u prime plus weight of u prime v prime is less than the distance of u plus the weight of uv. There's your contradiction. This is a contradiction. Okay? So I hope this argument makes sense, right? Any questions about this? So what is it that is, what am I arguing? I'm arguing that if you take the min of this quantity, which is v not in S, u in S, of du plus weight uv. Remember, du, you imagine, is known because for everything in S, you already know what the shortest paths are. So you're saying, let me look at everything where I know the shortest path, take one edge that goes outside, and take the minimum over all possible choices. And if I look at that minimum, or rather the argmin, that's an edge, that edge must be in the shortest, that is in the shortest path tree. How do I argue that? I say, well, let me look at that edge. So if I commit to that edge, I'm saying that the shortest path from S to V is S to U, and then go to V. And if there was any other way of getting there, it only has to be longer, because if it were shorter, suppose it was shorter, so it goes from, so you're going a path that goes from S to outside of S. So there has to be the last time that it leaves S. So U prime V prime is the last time that it actually leaves S. Right? So this is the in S, not in S, and then everything else is not in S. This is the last edge that crosses that cut. And then you say, okay, so therefore so what we're saying is that the distance to V, the true distance, this is like the true distance, is the distance to U prime, which is known, plus the weight of U prime to V prime, plus the distance of V to V prime. And this is less than, because we argued that S to U to V is not a shortest path, so it's less than du plus weight uv. And then, of course, because of the non-negativity, the distance from V to V prime is greater than or equal to 0. And so then you get your contradiction, because actually then this implies that uv was not the argument. Do you have your hand up in the back, or no? Okay. Yes, does this make sense? Okay, this is short of a formal proof, but essentially it shows you the basic math. You can use this to sort of complete the proof. Okay, so of course I haven't told you how to implement Dijkstra yet, but you'll see that that's actually a fairly, I mean it's clever, but it's essentially, it uses the idea of prim. Yeah, go ahead. Huh? It's a good question. I don't know. Maybe prim. Although Dijkstra supposedly came up with this in half an hour or something. Like he was thinking about it and he came up with it. So, I mean, yeah, in some sense, research was a lot easier to do back then, right? All you needed was about half a page of math, and you had a paper that would make you famous. But not any longer, I guess. At least not in computer science, not in algorithms anymore.
To finish finding all the shortest path, do you just keep doing this for all V not in S?
I haven't described the algorithm yet. But yeah, essentially, okay, you could imagine if you repeatedly computed this argmin. Every time S is constructed, you could do the argmin. Then that would give you the algorithm. Right? Because every time you compute the argmin, you find one more edge in the tree, and you only have to do this n times, or n minus 1 times, and you'll get all the edges of the shortest path tree. But the question is, how do you compute this efficiently? Like, you don't want to repeatedly scan over everything. So what we'll show is that essentially if you maintain a priority queue, a binary heap, the right way, then it's easy to compute these things. Like log n time, you can get the next one. Questions about this? Hopefully this is clear. Any questions about how Dijkstra? So I want you to sort of, whatever is written in that box is the key to me. Right? What's nice is if you actually replace that du, and you just do argmin, and that's shortest paths. Sorry, that's minimum spanning tree. And you plug this in, and then you get shortest paths. So clearly there's some underlying principle that's more general, and yes, because this is all doing some kind of a particular optimization. If you go more into optimization theory, you'll have like some unifying frameworks to talk about these things. All right? Okay. So let's now do the implementation of Dijkstra. So let it come into focus. There. Okay. Okay, so implementing so it's useful then to take sort of the opposite view, or the opposite view is to say that, well, I don't know if the opposite view is the right thing, is to say, okay, so suppose here's your capital S, and suppose you found the next vertex in S, right? So this was the UV that I talked about. So what you do is essentially the next vertex that you're going to get is always a neighbor of something in S. And what you did was you just extended S by taking this in. So just look at all the neighbors of that vertex and do an update for each of these. Right? So every time you get a new vertex, it's like some amoeba that's growing, right? Every time you get a new vertex, you basically look at all of its neighbors, and then you just do a relax operation on those edges. It's as simple as that. Yeah. Question?
This is something where I'm actually not sure. Like in the normal implementation, if V has a neighbor that's inside of S, you need to update its.
So what you do is, I mean, you're just doing a relax operation.
Yeah.
You don't really need to up. What do you mean by a normal implementation?
Well, I guess like I'm just like if V has a neighbor that's in S.
Which it does, like you.
Or sorry, maybe a different neighbor.
Okay, sure.
Like often you'll update. Oh wait, no, never mind.
You're just doing a relax operation. So technically you can even just not. You don't have to maintain anything in S anymore.
Yeah, you don't care.
So it's just you're maintaining a priority queue, and what you're doing is you're just updating the weights. You're updating the priorities of these neighbors by doing a relax operation. So let me say, so we'll, initialize the set S just to be the singleton vertex S. So you set D of S is equal to 0, D of V is equal to infinity for S not equal to V. And then you create a min priority queue over the vertices where dv is the priority. Right? Actually, I should probably, let me just initialize this to the empty set. And then what we say is, while, so I'll call the Q, while Q is non-empty, step 1 is extract min from Q, call this vertex V. Right, so you extract it, you add V to S, and you could also output the current dV at this point, because that means that you know what its distance is. And then what you need to do is So you've added v to s. Then you look at all the neighbors. You apply relax operation. So for every, so I'll call it w in the out neighborhood of v. So call relax VW. So this is W here, right? So you call relax on each of those. And this operation, so if relax we reduced TW, then you update the priority of W in the queue, right? So you have to reduce the priority then, because it was a min heap, so the priority reduced.
Wouldn't you need to add before step 4? Wouldn't you need to add the first, S inside Q?
So actually, Q has everybody in it. And ds is 0, so q it's at the root, right? Make sense? Yeah. Okay, does this algorithm make sense? Yeah.
What on step 4.2? What is outputting DV?
I'm just saying, like, you print it out or whatever, because if I don't put this, then you might say I'm not okay. So because I'm not maintaining predecessor pointers, I'm not really storing. You could also maintain predecessor pointers through if every time you do a relax. Okay, so I guess another way of doing this is to just say that you can output that in the predecessor pointer according to the relax operation. Yeah, I'm being a little sloppy about the output itself, but you could see that the predecessor pointers as maintained by relax will be the shortest path tree. I guess my point simply is that at this point, whatever dv is the shortest path distance. Any questions? Okay, so let's just look at the running time. So running times are steps 1, 2, 3. It's just O of n. Like, you can build a priority queue over a bunch of things in linear time. This step over here, this is going to cost you log n. And this step over here, the update, is also log n. Everything else is fairly straightforward. How many times do you extract? You can do this at most n times, right? Because there are n vertices, and you extract a vertex. So step 4.1 in total is O of n log n. Step 4.2 is just O of n. You're just doing some standard operations. Step 4.3, because for every vertex, so when v gets extracted, you look at all of its neighbors and you call relax. So this is just O of 1. This is just an O of 1 operation. So for every neighbor, you may potentially update the priority queue. So how many updates are you doing in total? M, right? Because for every edge, there's one update. Step 4.3 is for every edge, at most single update to priority. And so this is O of m log n. So the total is just O of m log n plus n log n. Okay? Now, it's a more advanced data structure, but if you use something called a Fibonacci heap, you can actually get rid of the log n here. It uses something called amortized analysis. So what happens is some priority updates are actually expensive, but in the average, it's actually going to be constant. It's a much more complex data structure. Fibonacci heaps will get rid of the log n. But I think in practice, people rarely use a Fibonacci heap. A binary heap is good enough. Okay, so this is Dijkstra. So again, if you kind of zoom back, ignoring all of these things, the only place where the distance gets updated is by a relax operation. So it's really coming up with the right sequence of relax operations. Unlike Bellman-Ford, which just sort of does it blindly. But this ordering of relax operations is exploiting the non-negativity of the weights. All right? Okay. So this is actually a good time to pause. It's 12:23, so let's pause for maybe a few minutes, stretch your legs, switch your phone off, whatever, and then when we resume, we'll do all pair shortest paths. Hello? Okay. Why don't we continue? Is this too loud? Is it fine? Should I decrease the volume a bit?
Maybe a little bit.
Hello? Is that better? Maybe more?
That's good.
Yeah? Okay, good. All right, so we've done single source shortest paths. And now let's do all pairs shortest paths, known by the acronym APSP. So this is the problem is you have to output what's called the distance matrix D, where the distance matrix D of UV is the distance from U to V. So there's no one source, right? You have to look at all possible sources. So find the distance from everywhere to everywhere. This is the distance between all pairs. Note that in this case, the output size is quadratic. Right? The output itself is quadratic, so we might as well think of the input as quadratic. There's no need to use an adjacency list. So typically, we will use an adjacency matrix input. And what we can do is we can set the weight of UV is infinite if UV is not in E. I'd say if there's no edge, then the weight is infinite. So maybe to answer your question, think of weight as like, that's the distance in one hop. Right? Okay. So the weight. So we use the adjacency matrix input. Why do we do that? Because the output itself is n squared. So you might as well imagine the input is n squared. This will be convenient, this matrix, the adjacency matrix representation. Okay, so this is okay, so what is the obvious way to solve this problem? Well, you could just run a single source shortest path problem from all sources. Right? So the obvious algorithm is run an SSSP algorithm from all sources. So for general weights, this would be n runs of Bellman-Ford. What you get is theta of mn squared. So if m was quadratic, this would essentially be quartic. It would be fourth power. And for non-negative, you would do n runs of Dijkstra. And what you would get is, I'm just going to assume, well, I should call it O and not theta in this case. I'm going to assume that m is at least n. Just assume it's connected, right? Because otherwise you could just do it separately for every connected component. So you'll get n times what we had before. So you get n times that quantity. So you'll get mn and n runs of Dijkstra. So again, the question is whether you can beat these bounds. So in general, okay, so here's what we can show. So before I launch into before I tell you Let me first tell you what results are there. So you can use, essentially there are two approaches. One is called the matrix multiplication, and there's a similar method called the Floyd-Warshall algorithm. These are both, technically they're different, but what they'll give you is you can get something like O of n cubed. Technically with matrix multiplication it's n cubed log n, but think of it as O of n cubed with some logs. With Floyd-Warshall it's n cubed, matrix multiplication is n cubed log n. So this works in general. Now suppose M is O of n, M is sparse. Right? So typically this is saying that the average degree is small. This is your social network. In your social network, your average degree is small. Right? If you pick your average, you pick a usual Twitter network or a Facebook network, there are a few billion vertices, or maybe many hundreds of millions of the average degree is maybe about 10, 20, maybe it's about 100 at most. Right? And so n cube is too much. Mn log n looks much better. So there is something known as Johnson's algorithm, which gives you O of mn log n for general weights. So what's nice is it basically gives you whatever Dijkstra can give you, even when weights are general. But the annoyance is that this only works when you want all pairs. If you only want a single source, then this is too much. So it doesn't let you circumvent the problem of Dijkstra for a single source, but it allows you to circumvent when you want to do all sources together. So these are, I mean, this is like a lot of people study this problem, people try to improve things, but by and large, the cubic bound has, okay, there are ways of beating the cubic bound. You can improve on the cubic bound, but the core ideas are sort of similar. Like basically how people beat things is by doing variants of some of these ideas. So let's see how far I can get covering these things. Maybe the important thing I want to tell you is how matrix multiplication enters this computation, which I think it's quite fascinating. Okay, so for the sake of discussion, let's assume graph is undirected. We don't necessarily need this, but it will make a lot of our discussions easier. So what this means is WUV is equal to WUVU, symmetric, and also it means that the distance from U to V is equal to the distance from V to U, because any path from U to V is a path from V to U and vice versa. Okay? Let's go back and look at the basic recurrence. So we could just start with this basic recurrence for distance. So let's say dk of uv is equal to the distance from u to v using at most k edges. Right? Just as, and I'm going to assume there are no negative weight cycles because you could run Bellman-4 to first check that. So if you recall, the recurrence is, for this is d1 of uv is simply the weight of uv. And dk of uv is the min. I'll just say over all vertices w. Well, w is annoying. We can't use w because w is weight. u, v, let me use x, sorry. x. You know when your paper is really long, and this has happened to me, when you run out of symbols. Then you move to Greek, you start running out of those as well. That's when you're in real trouble. And it's happened once. Now actually I had to look at the Greek alphabet and see if there was something that was left. But then it becomes confusing because x, you think of x prime as a version of x. If x prime is something completely independent of x, then I actually saw someone do this in a proof. There were three sets st and u. Little t was an element of capital S. And little s was an element of capital U. And you're like, I said that paper had to be rejected at that point. Okay, so x, so you take the minimum of x of the distance of k minus 1 from u to x plus the weight from x to v. Yeah?
Why do we do it this way instead of the other way around? I guess there's no reason.
For, which way?
I mean, like the distance of k minus 1 from x to v, and then the w of u to x.
I guess it's the same, right?
Yeah.
I'm assuming it's undirected, and yeah, it's the same. I'm just thinking, I'm using the same. The picture that I had last time was looking at the in neighborhood of v, so I'm thinking of this being like, I want to get from u to v. I'm looking at x being the last step.
Yeah.
So then I get this. Okay. Okay, so this is the basic recurrence. So we could just go ahead and solve this basic recurrence just to see what we're going to get. So note that our dynamic programming table now actually has n cubed things because there's u, v, and there's k. Right? So if you do the dynamic program, the table has n cube, well, O of n cube entries. Because there's u, v, and then there's k, and k goes from 1 to n. So the table, I said the table has all of n cube entries. Each entry takes O of n to compute. Because you have to do this min. You have to do the min. So total is O of n to the fourth. O of n times O of n cubed. Of course, if you're more careful, you can also make this like instead of mn squared, because you're basically doing Bellman-Ford n times. It's the same thing as doing Bellman-Ford n times. Okay. But I want to give a different perspective to this. And with this perspective, well, I don't know, I hope you'll have an aha moment when you see this. Let's go back to this expression. Okay? Okay, so let me now construct matrices. Let me say that the matrix that I will refer to. Okay, so I'm sorry for pulling this off on you. I'm going to move this to a subscript as opposed to a superscript. It doesn't change anything, but for the matrix, it's going to be useful. So what is dk? dk of uv is simply this, right? So this is, I'm thinking of as a matrix. Maybe you want to put it this way. So this is dk here. Okay, this is dk. All right? Now I want to get all of this on one page together. So okay. Heck, I'm going to write this thing again over here, right? So dk of uv is the min of x in v, dk minus 1 ux plus the weight of xv. And let me over here just put the weight matrix, which I'll refer to as capital W. It's like the adjacency matrix. Now, look at this computation again. You can think of it as follows, because I'm also going to use some kind of symmetry here. So let us look at this as the row corresponding to u. So this entry over here, if I look at the exit entry here, this is just dk minus 1 of ux, right? That's exactly what you have at that row and column position.
Wait, shouldn't it be dk?
I'm sorry. That was an easy fix. Now you're adding that to wxv. Okay? Now because this is symmetric, if I look at the xth column here, no, I'm sorry, I was the other way around. No, this is fine, sorry, I'm doing this right. You can always mess things up when you're doing things. Actually, one doesn't even need the symmetry here, but, and if I look at the xth row here, what I get over here is wxv. Do you see that? Like if I look at the row corresponding to u, I get the first thing. I look at the column corresponding to v, I get the second thing. So actually, I don't even need, you don't even need the graph to be undirected. This is unimportant for that. So this looks a lot like if you were to instead of this, suppose I did the sum of dk minus 1 ux times wxv. Suppose I did the sum instead of the min. I did a multiplication instead of the addition. What is this then? This is just matrix multiplication. So one can interpret distances as matrix multiplication over a different operation. It's a different ring. So we'll keep this picture up, I think, because this picture is really important. So matrix multiplication you can think of as over this times ring. We have addition and multiplication as like the fundamental operations. Distances is over. So you replace the plus with a min and the times with a plus. This is not, it's like this is like a semi-ring. It will satisfy a lot of the, okay, so how many of you have heard the term ring? Okay, so many of you have not, that's fine. So think of ring as basically just like a bunch of elements with operations on them. Just like you think of numbers and you have these operations on numbers. Well, I can also do the min operation on numbers. I can do the plus operation on numbers. And I can kind of, as long as I have things like commutativity, which I have commutativity here, you have associativity, you need to think about the distributive law, but you could think of all of the properties that you have that you learn in arithmetic, I don't know, in grade school or whatever, and apply them to a different sequence of operations and whether it holds. And when a set of operations holds, you can call it a ring. This isn't exactly a ring, it's something called a semi-ring. One can spend like, decades studying this, But what's important for us is, what's nice is the moment you replace those operations with these, you get shortest path distances, which is really neat, right? So when you observe that the operation being done by the recurrence is essentially like some strange form of matrix multiplication, we can say that dk is kind of equal to dk minus 1 times w, where you're doing matrix multiplication over min plus. Right? And d1 was just w. Your final distances, the final distances, is equal to d, basically is dn minus 1. And because anything is dn minus 1, which is just w to the power n minus 1. So all you need to do is to find this matrix. Okay? Now at this point, there's no obvious improvement over here, because each multiplication matrix multiplication costs O of n cube. And because if you just do this multiplication, each multiplication costs you n, because you have to go over the min, and you do it n squared times. So it's n cubed to do a single matrix multiplication. And if you do n of these, this is going to be, the time is O of n to the fourth. So we just redid what we have all over again. But this perspective is very useful. And note that even if you did d of something larger, so let's take, let me see if, yeah, so maybe you take d of r. So for r greater than or equal to n is just equal to d of n minus 1. Right? Does that make sense? Because even if you go further and further off, it really doesn't buy you anything.
Assuming there's no negative.
There are no negative weight cycles. Otherwise, distances are not defined. So it's like a strange multiplication, right? You keep multiplying, and then at some point, you don't get anything. But this property, together with the multiplication perspective, is going to give us the faster algorithm. So the faster algorithm for APSP, this is a very important trick or concept, is you just do what's called repeated squaring. So the idea is compute w, then w square, w to the fourth, w. So what you do is you keep squaring it, and you can keep doubling of 2 to the I until at some point you'll get to 2 to the log base 2n ceiling, and this is going to be equal to your distance matrix. Does this make sense? Right? Where w 2 to the I is just w 2 to the I minus 1. Matrix multiplication, this is the matrix multiplication over, min plus. Very clever, right? Maybe this went a bit fast, so I hope you're following. Yeah, go ahead.
So like when we're doing the multiplication, are we like swapping
saying like the plus and multiplication operation?
Yes.
Like that's just it?
That's it. Like, yeah, or rather, you're basically just replacing plus with min and times by plus. Right? So you're just taking a matrix multiplication code. I mean, okay, so you have to be careful. You can't take something like Strassen, which does something weird. Take a basic matrix multiplication. Take the n cube matrix multiplication, which just like going over, I mean, it's just basically doing a for loop over all x. So in that for loop, you go ahead and modify the operations. I'm not writing out the entire code over here because to some extent I want you to see the pictures instead of seeing me writing out all the little code. I'm happy to explain more if there's any confusion. So CLRS has like the code given in fairly gory detail with all the indices and everything. But I think the important thing for you to see is, okay, so just to recap what's going on here. We started with our basic recurrence that is here. So we started with this. We said, let us interpret the operation of going from k minus 1 to k as a matrix operation, because we're storing all these values for k minus 1. And then we observed that the min plus operation, it's almost like a vector product. It's almost like a dot product. It's just dot product over a different operation. Right? So you replace the summation and the multiplication in normal matrix multiplication by min and plus. So it's almost like min, you think of, it's weird, you think of min as summation and you think of summation as multiplication. Right? And so what that does is that then gives you a matrix perspective, where the matrix perspective is that dk is dk minus 1 times w, where w is the weight matrix. Again, I misspoke in the beginning. You don't need, this works even when things are directed. Right? Everything checks out. And so that means the distance matrix is really the n minus 1th power of the weight matrix. But you can power it even more and won't make a difference. Because remember that dk is the distance from u to v at most k edges. So you can use more than k, you can use more than n edges, it's still at most. So when you start powering beyond that, it's not going to make a difference because you already have the distances. And so then what you can do is you can do matrix multiplication. So then you're saying, okay, you want this nth power. And instead of doing it sequentially, which is w1, w square, cube, 4th power, 5th power, do squares. Just keep squaring your matrix. So start with the matrix, square it, square, square. And once you do log n squaring operations, you end up with a distance matrix. So each squaring takes O of n cubed time, and you do basically log base 2n squarings for a total of O of n cube log n time. Right? So it's a pretty big improvement. From n to the 4th, we get it down to n cube log n. Yeah?
This is basically saying, like, if you want the paths of length 4, then every path of length 4 is made from 2 paths of length 2.
Exactly. So I was actually going to say that. One can interpret this as a different recurrence, which is saying that if you want a path of length at most 2 to the I between two vertices, look at a path of length at most 2 to the I minus 1 to some intermediate vertex, and then a path of length 2 to the I minus 1 after that. So the picture is, so I will explain that, but first I want to make sure that you understand this. Any questions about this? I don't know, the first time I saw this, it blew my mind. Right? It's just completely like, wow, okay, that, I didn't expect that. But when you kind of step back and think about it, if you think about what matrix multiplication is doing, and you think about the nth power, you'll start seeing that it's actually computing paths. So there's actually this tight relationship between paths in a graph and powers of a matrix. Yeah, questions? This is what you get in education for, to see things like this. Okay? All right? Okay, so that gives you n cubed log n. Now, as was pointed out, I can reinterpret this algorithm in terms of a different recurrence and go back to a dynamic programming perspective. Okay? But this is the matrix multiplication perspective. So you're doing log n squarings of a distance matrix. And the squaring is a matrix multiplication over this min plus. I should say something here, which is something that, I didn't want to go over the details of this, which is, you can't replace this by arbitrary operations and hope this works. There's some properties of min and plus that allow it to work. It's commutative, it has some associativity properties. Well, I don't know if commutativity might not even be necessary here, but for plus, definitely, yeah. So the first operation needs to be commutative. They're all associative properties. There's some distribution law that's going on. Like, all of this is happening under the hood. So if you wanted a really formal proof that all of this works, you'd have to check all of those operations. But I think that to some extent that's a manual check, meaning that it's more of like, okay, you go and sit down and verify it. The main thing is to see the pictures, to really see the correspondence between these, where the first is in the box is shortest paths, the second one is matrix multiplication, and you need to see that correspondence. All right? Just to give another dynamic programming perspective to this, okay. What we have is a dynamic programming perspective is to say that d of 2 to the I uv. So what is this? This is the distance between u and v of at most 2 to the I edges. Remember previously, okay, so I should write that. Previously, x was the predecessor on the path. But it seems like another choice would be to take x as the middle of the path. So then this portion has at most 2 to the I minus 1, and this has at most 2 to the I minus 1. There's some x in the middle, where the portion from w to x is at most 2 to the I edges, I minus 1, and the portion from x to v is at most 2 to the I minus 1 edges. Right? So there's some portion there. So you could just take this, sorry, run out of ink. Is the min over all vertices x of d of 2 to the I minus 1 ux plus distance of 2 to the I minus 1 xv. And if you take this recurrence, then you exactly get the repeated squaring. So this is equivalent to repeated squaring. All right, so this is a dynamic programming perspective. So we could have actually re-derived the previous algorithm without talking about any matrix multiplication by just showing this recurrence and then just doing a dynamic programming table for this. Because you'll see your dynamic programming table now, instead of having n cube entries, just has n squared log n entries, and each of them is computable in O of n time. They're both equivalent. Any questions about that? It kind of says that because you have so much information, this is sort of not using all the information that you have. And this perspective of taking the midpoint is using the information more efficiently, and hence it's a more efficient algorithm. It has, I'm stretching a bit, but it's kind of like linear search versus binary search. So some kind of like a binary search perspective to it. Like get to the midpoint and then get from the midpoint, rather than go all the way to one end and then take another edge. All right? Questions? Questions about that? Clear?
We can't just do this to Bellman 4 because it involves like another distance for
Good question. So,
different starting point.
yeah, exactly. It involves this from a different starting point. What you can start doing is, if it's undirected, then what you get is symmetry. So you can actually flip the v and the x, which means that then if you're only trying to get the distance from u to v, that's all you care about, then what's nice is it kind of has this thing of you only need to do, okay, so this is like, it's like a meet in the middle approach. You want to get from u to v. Instead of going, what you do is you go backwards from u and forwards from v, and you kind of see where they meet. And sometimes if you do that, in the worst case, it's not going to help you, but in many cases in practice, it actually gives you an improvement. So this is called like a meet in the middle approach. I've actually done this sort of idea relatively recently in my research work as well. Like you're trying to find paths in a social network between two people, you want to find short paths. Instead of trying to crawl from one, if you do a backward crawl and a forward crawl, and you see where they meet, you can often save a lot of running time. But this connection between paths, matrices, powering is much more common than you might think. Indeed, if you've ever heard of the term Pagerank, which is what Google's, now it uses lots of things. One of its core algorithms when it started off into ranking pages was basically about understanding paths in a graph, right? It says that if you have lots of paths that lead to one website, then probably that's an important website. And how do you discover these vertices that get lots of paths? You set it up as a matrix problem. And then you do some matrix computations. And then you try to distribute those matrix computations and so on and so forth. But this connection between paths, matrices, graphs is like very, very important. It comes up over and over again. Okay, so the last thing that I wanted to talk about was the Floyd-Warshall algorithm, which is, one way I like to think about it is you want to get an even better dynamic program. Right, so just like we started with the basic dynamic program, got n to the fourth, improved the dynamic program, got n cubed log n, we can do a further improvement and get n cubed. This is very clever. So it says, instead of looking at the number of edges on the path, let's parameterize by something else. So I'm going to refer to this as d, and now I'll use a superscript to distinguish. I'll put it in parentheses. I'll say dkuv is, this is very bizarre, is the shortest path distance between u and v using paths that only involve vertices at most r. So this is, I'm looking at the label of the vertex. So think of it's convenient to just think of the vertices as labeled from 1 to n. So this is saying let druv be every intermediate vertex here has to be at most r. Its label has to be at most r. Does that make sense? So it says that you're almost, u and v might have labels more than r. It's almost like saying just focus on all the vertices whose label is less than r and only use those to get a path. That's what dv of r is. So if r is equal to n, then of course this is the main distance. So the distance is just the distance dn of uv. Now this is the really clever bit. So let's write, if we write the recurrence. So let's write the recurrence for dr of uv. So this is the min of, so you're only looking at the path where you're looking at things whose label is at most r. So either you never used anything at most r, else what happens? You must have used r on this path somewhere. So r is somewhere here. But then everything in between here is at most r minus 1 because r is only used once. You're looking at all the paths where all vertices have a label of at most r. If r is on the path, then everything else is at most r minus 1, obviously. So this is saying this is the min of dr minus 1 uv and dr minus 1 of ur plus d of r minus 1 r v. So that is brilliant. So what is so brilliant about it? Well, now this min is just a constant time computation. It's actually like one of the worst things to give in the last 5 minutes, and everyone is tired and can barely follow. But maybe I should have given another caffeine break in the middle. Like, go and get some caffeine so that you can. Okay, so what is this saying? It says, I will keep this here, but I will write something. Okay, it says, consider the shortest path from u to v using only, okay, so using vertices, using vertices whose label is at most r. It says there are two cases. So case 1, the path has vertices of label at most r minus 1. So it actually never uses r. Path does not use r. Sorry. Yeah. So the path does not use r. So here's u, v, and if it doesn't use r, then everything is at most r minus 1. And this is exactly dr minus 1 uv, case 1. Either this or what you have is case 2. The path uses r. well, either it doesn't use R or it uses R. It has to be case 1 or case 2, which means, but all other vertices have a label of at most R minus 1. So what this means is U